Hey Matt, how you doing? Hello, 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 hello. Yeah, it's working.
Hey, Professor Younger, how you doing?
All right, how's it going, Matt?
Pretty good.
Were you the one that went to take the test on Monday? Or
I
no,
did
that
not,
was my
no,
241 student. Okay,
no.
good. I was afraid. I actually had some problems with my tests, and I submitted them for every day this week, and a student showed up like yesterday. Yeah, around like noon or something, and the test had messed up, so I didn't have
Oh,
it
okay.
ready. So
Okay.
the first name was Matt, but I think it was a 241 student. Come think of it.
All right.
Glad to see you
Yeah.
back.
Yeah, thanks. Thanks. Getting caught up with everything. Just want to make sure that I'm clear. We have a face-to-face and an online test due by Monday. Is that correct?
Yeah, and actually, I went ahead and made it Tuesday because of the problems I had with the test. So you have actually until Tuesday of next week.
Oh, okay. Great.
The way it works is, remember, one's online, uh, and you have until 11:59 p.m. Tuesday to do that. The face-to-face one, you have to get proctored, but you have until 11:59 there as well.
Okay. Yeah, sounds good. Should be able to knock that out.
No problem.
Like I
I
said,
did.
still
I
on
should
target.
mention one of my students asked about this in another class, so I want to let you know. I've been trying to make sure we had ways where students don't have to actually pay, but there are third-party services that you can pay to have them proctor your test via
Okay.
like Zoom and a camera and stuff like that. Uh, or I tried to get our testing center to do it, but they couldn't do it because they couldn't lock down the browser and watch you through Zoom. Uh, but they're working on a way to do it, so hopefully, eventually, that might be free too.
Okay. Yeah, sounds good. At least for my part, I won't have a problem getting to the one of the
Cool.
campuses.
Well, let me know if you have anything. Hello. I love kids, so it's all cool.
I'm going to be in class. Okay, sweet. Yeah, I did have a question on one of the videos on capacitance, just on the concentric spherical
Hmm.
capacitor, and really my question is, and I apologize, I don't have it in front of me, but my question is, when you going back when you analyze the electric field for the parallel plate capacitors,
Right.
you the electric field was actually double, right? Two
Yeah,
uh
because one's
yeah,
adding to the
yeah.
right and the other one's adding to the to the right as well.
Yeah, yeah. So my question was, why didn't you take that step on the concentric spherical capacitor?
That's actually a really good point. It turns out, and we learned this from Newton in the chapter on gravity in 241. It turns out that when you have a law like Coulomb's law, which is identical in mathematical structure to Newton's law of gravity, that any mass or charge farther away than you are from the center of the mass and charge can't affect you at all in making the electric field, or in the case of gravity, the gravitational field.
Okay.
So
Okay.
the charge on the inside of the spherical shell would be literally on the inside of the spherical shell,
Mhm.
and it can't affect any electric field at r smaller than the radius of the inside of the shell.
Okay. Interesting.
Yep.
Then yeah, that explains it.
Now that is a good question. I'm glad you asked. I'm actually really glad you did because no one's ever asked, and that is actually an excellent question.
Good. Yeah.
I guess we
Kill
should
my
go ahead and get started, even
vision
though it's
here.
just you.
Yeah. All right. Sounds good. And I have to confess, I'm still getting caught up, so I haven't really dug into the materials yet, but follow along as closely
No
as I
problem. This chapter four
can.
stuff, the three-step paradigm that I keep telling
Mhm.
people about, that
Yeah.
often comes up where you take Gauss's law, usually it's Gauss's law, in principle it could be Coulomb's law, and you find the electric field for the parts of the capacitor that you're going to study. Then you use V equals the negative integral of E dot dl to find the voltage between the negative plate and the positive plate. And then the third step is you use C equals Q over V to
Yeah.
calculate the capacitance. That seems scary to people, but it's pretty straightforward. And normally we have two or three of those types of problems throughout the whole semester, midterm, one test, a final, that sort of thing.
Okay.
But let me know if you need any help with that. It's really just a process you sort of memorize initially and then understand it later.
Yeah, I get the process, understand it. It's getting to E that is hard for me through the first step. Getting all the way through that without a mistake is
Yeah, that
tough.
that Gauss's law is weird the way you have to apply it, and it's just some trickery. I mean, when I took the algebra-based physics, they didn't offer that as a sort of thing that you could do, but nowadays in the algebra-based physics, they make you do it too, even though you don't have any knowledge of calculus whatsoever. So it's really crazy, but that also leads you to probably reach the conclusion that maybe if you looked at an algebra-based text for that section, it might make more sense and be easier for you. So that's
Okay.
something to give a
Yeah.
try. We have some in the library, but they're normally just books called college physics or just
Mhm.
physics, but they don't have the scientists and engineers part for it.
Okay. Got it.
Okay.
I guess that leads me to a question about the face-to-face tests. I noticed from the last one that we actually turned in the notes. That's and you've referenced in the videos a couple of times. I think kind of getting those three steps down on paper. Is
hmm
that something that you look at? I mean, is that
Yeah,
literally
so what
something
I
that would
often
make
do with a
someone?
test is I'll take a question that looks like one of the test bank questions. In fact, it was one of the test bank questions where it said, here's a parallel plate capacitor, what's the capacitance or what's the energy stored in it and stuff like that. And I take it and add descriptors that make it like a Socratic question where it'll say, use Gauss's law to find the electric field. And
Yeah.
it'll give you a couple hints. And then it'll say, step two, use delta V equals the negative integral of E dot dl. And what happens is when you're done with that, the multiple choice part might be worth 2 points, but the other 10 to 15 points might be worth all for the work that you turn in.
Yeah. Okay. Oh, okay.
So that's what happens. Whereas normally I don't necessarily even collect the work. The only thing I collect is if someone wants to bring their own formula sheet to the face-to-face test, then I ask them to send me that so I can make sure that that's no more than what I give them in the test.
Okay. Yeah, so just to be clear, so you do collect the work on some questions.
Yeah, on those types of I do,
Okay.
and it's usually just one or two, and it'll say it right in the question. You'll know it when you hit it.
Okay. Yep. Got
Yep.
it. All right. Cool.
That's another
Um,
excellent question. I'm glad you asked me that because no one ever does, and I know I mean to say it and tell them, but I often forget.
okay. Yeah, I'm gonna kill the video here and the audio. We can start. I'm gonna
No problem.
follow along.
Thanks again, Matt.
Yep. Thank you.
All right, everyone. We're starting chapter 25 now, and chapter 25 is called Electric Current and Resistance, and it starts off with the electric battery. So I thought I'd give you a little description. Excuse me. Of how we go about making a battery. So Galvani in the late 1700s discovered while he was messing around with frogs that basically he could make dead frogs' legs twitch. And even to the point where it's dead frog's legs without the rest of the frog could actually twitch. And some people thought this was quote unquote the life force or the spirit or the soul of the animal, that sort of thing, for a little while. But eventually, we were able to uh, more or less rule out any kind of stuff that we couldn't track down. In other words, ephemerate things, that sort of thing. So what ultimately it turned out to be is they discovered that when you have dissimilar metals in a aqueous solution in some kind of liquid solution where ions could exchange, ultimately. We learned it later that it was because of the ion exchange. But when you had the similar metals, that actually caused a difference in voltage. And because of that difference in voltage for the different metals, that would actually cause a current to go from one metal towards another. And that was the actual cause of the frog leg jumping. We now know, in fact, that we have sodium channels and potassium channels and calcium channels from a biochemical standpoint that explains to us specifically how electricity is used in the muscles of the heart and the bicep, the tricep, the traps, all those things. So that came from all of that, and then later. Volta was able to use that to create a battery. And you can look, for instance, I'll double check what page and figure it is. In figure 25.2, they have actual Volta's uh, diagram of his Volta. What did he call it? His voltaic battery. That's what he called it. So we named it obviously after Volta, but basically what it was, he tried to employ this different metal scenario that we learned from Galvani, which is now the galvanic process. Which, if you happen to own a boat, you probably have heard of the galvanic process because you often will buy little bits and pieces of metal to put on your boat in hopes that it will stop eating your lower unit or your propeller and stuff like that because of the different types of metals in the water and the little bit of salt in the water and that sort of thing. But the way to make it, I work at I was a founding member of a hands-on science museum in Elizabeth City, North Carolina, and I sometimes do shows there, and we will let kids make their own batteries. And one of the ways you can make a battery is you can take like a prescription bottle, like, this is actually a pencil eraser, but it sort of looks like a typical prescription bottle. But if it really was a prescription bottle, which luckily I don't have laying here because I'm sure I just put it up here and let everybody know whatever malady I have. But basically, you could take the lid off, and you could imagine taking a penny. Pennies are not copper, but they're coated in copper, and you could, in some sense, solder the end of a wire to one side of a penny, and then you could take the side of the penny that's soldered to the wire, and you could put that down, facing downward, in the bottom of the prescription bottle. And then you could take, the way I do it is I'd actually put like a little bit of gauze between it, cotton fabric or something like that, or even literally just gauze. And I'd put it down on top of the penny. And then on top of that, I would put like a quarter or a zinc washer would work. Any metal other than copper would work. And then after putting that on top of the cloth, at that point, I literally already have a battery just as long as I add some liquid in there. Now, what liquid do you add in there? In principle, anything but distilled water would work. And then distilled water could possibly work as well. The main problem is when you distill water, you often get rid of all the little things that can become ions in the water. And if you do that, it's actually not even safe to drink in copious amounts. They've had people die from drinking water that's been distilled because it literally dilutes your blood and makes the ion count too small so that your muscles, specifically the one for your heart, can't work too well. And, obviously the heart's kind of essential for your body working. But either way, if you took water in there, that would be one source, as long as it wasn't distilled. You could take vinegar, you could take water with a little bit of lime juice, you could take lime juice, you could take orange juice, just about anything, pool water, salt water, just about any liquid, and stick it in there. Okay. And now if you touched a voltmeter to the wire that's soldered to the bottom of the penny, and then the other probe for the voltmeter, and stick it on the side of the quarter or the zinc washer that's on top of it, that alone would give you a voltage reading on the order of, zero point 0.2 volts or something like that. Not a huge amount. But, and this is partly why the diagram's drawn the way it is. But if I, took that probe out that I was touching the quarter or the zinc washer with, and I stuck another piece of cloth. Again, this is just the way I do it. You probably could do it without the cloth, but I always put the cloth in there, and then put another penny, and then another piece of cloth, and then another zinc washer or quarter, whichever one you're using. And now, if that first reading was zero point 0.1, if you did it now, you'd get zero point 0.2, and you could add another one and another penny and another piece of cloth and then another zinc washer or quarter, and then you'd measure the voltage again and you get zero point 0.3, and it sort of keeps on like that for a long time, but you could keep stacking them on top of each other, on top of each other, on top of each other, and as long as you have some kind of liquid to carry some of the ions from place to place to place, it would probably work. If you look at Volta's diagram, it doesn't, obviously he didn't submerge the different metals in things, but he does have the different metals against each other, and then they're ultimately connected to something that's like water or some kind of liquid. But the main thing is, in doing that, you can not only build a voltage source, but you can build it in some sense as big as you want. Yeah, obviously, there's going to come a point where if I just double it, it's not going to automatically double the voltage. It might do a little less than doubling, but still, it gets really, really high. And with that, that was sort of the first time we could slowly add power to something and watch it as power ran through a system for some time. Whereas normally it was just a matter of catching static charge that you get from, say, rubbing a rabbit's fur up against some amber that was basically just fossilized tree sap, something like that. So now with that, you could actually start to study circuits, and that's why such a big deal happened in the 1800s, specifically from the late 1700s to the early to mid 1800s was the time where Michael Faraday and Gauss and Volta and Hertz and all these different people were working on what now became Maxwell's equations. And in fact, Maxwell becomes the Lucasian Professor of Mathematics at Cambridge University, which is the same position that Isaac Newton held. It ultimately will be the same position that Dirac holds. Dirac is the person that predicted the existence of antimatter and did so based on the fact that he knew or was quite confident that this equation that he made up was correct. And the only way he could make sense of his equation being correct is to invent the existence of antimatter. So he did and said, "This is what we'll find." And sure enough, we found it. So that's another guy that got that position. And then most recently, the person that people have heard of is Stephen Hawking had that same position. After that, of course, a guy by the name of Witten currently has it, and Witten's sort of the person that created string theory. So just to give you a little bit of historical perspective on that, so that's kind of neat. But that's what came out of the 19 or the 1800s, and Michael Faraday, who really had basically a high school education, as much as they had high school for that period of time in Great Britain. But he was a type A personality. He was bound and determined to do great things, and he wanted to be a great contributing citizen. And I didn't even know this existed, but sure enough, he discovered a self help book in the library after he graduated, and it said, if you want to, be successful, you should learn a couple languages. You should master a particular field and stuff like that. So he took a real interest in chemistry, which luckily he found another book called Conversations on Chemistry. You can find that at Project Gutenberg, by the way. Very, very interesting. And it was written by a lady, which is a pretty big deal in the late 1700s, early 1800s when she wrote it, where she was married to a medical doctor, and her husband, being fairly wealthy, would travel around to see these great scientists doing demonstrations of science. And then she would write them in such a way that people could apply science specifically. Her idea was to bring it to the housewives and the women of the home so that they could find practical uses of science in everyday life, whether it be, laundry or cooking or cleaning and stuff of that sort, and just general knowledge. And between that book and his self-help book, Michael Faraday became a really brilliant, top-notch scientist, even though he had no education in math. And it sort of showed because he had shortcomings in math, but he could still picture things in 3D, and he pictured the way electric field lines oriented themselves. He imagined them as actual things, and magnetic field lines as they oriented themselves. And in fact, he made from his experiments, he made such a complete set of notes that James Clerk Maxwell, the Scottish physicist who comes in as the Lucasian Professor of Mathematics, reads his notes and is able to write down the four equations that we now call Maxwell's equations. The only problem was one of the equations was wrong, and Faraday had not discovered that. No one had discovered that. It was only someone who could put together the equations and see that there was an obvious way that this equation was not internally consistent. And because Maxwell was such a brilliant mathematician, he's literally the first person that mathematically told us exactly what the rings of Saturn were. I mean, people thought they were actual disks, and he basically showed them that that couldn't be. They had to be particles, and he predicted that some would be the size of buildings and stuff like that. So Maxwell did do this. He found the problem, he corrected and added the term to it, and then from there on out, those equations were called Maxwell's equations. They were put in a horrible format, though. They were first written in quaternions, which actually I have this book that I used to study for Jeopardy type questions and stuff like that. And it says, if you want to know what quaternions are, you're staying up past your bedtime, you need to go to bed. So that's what quaternions in some sense are. Now, I have studied them, and they were created by a guy by the name of Hamilton, who was around quite a long time ago, but not quite as long ago as Alexander Hamilton. So this is a great mathematician as well. But that was part of the reason that the equations were put in quaternion form, as well as they were using some weird potentials that scientists of the day were using, but turned out to not pan out to be that helpful. So Maxwell really had a problem with selling his four equations, even though he didn't actively pursue it, because poor Maxwell died of a horrible case of stomach cancer at like early 40s, just like his mother did. And it was just really bad, because that would have been the time where he would prove to the world that his equations were so perfect. And everybody sort of still had a really bad attitude about him, because he was what they call the second wrangler. So when people in Great Britain get to go to Cambridge, they do their 4 years, and then they have a Wrangler exam at the end of the 4 years. And everybody in the school takes this Wrangler exam, and it's like 8 hours straight of hell. And it's nothing but math and physics, or math and what would ultimately be called physics. So it's math and science and that sort of thing. And it's a really brutal test. And not only that, when they finish grading them, they hang the grades up publicly on the wall, with the highest scorer at the top spot, and the second highest in the second spot, the third highest in the third spot, all the way down to the hundreds of students, which is completely illegal nowadays, but that was the way it was done. And he came in second. And there's actually three of the types of tests like this, two or three of them, and no, it's two of them, and then something else that's unrelated. But Maxwell came in second place on that one, and the other one he came in first place on, and he went on to do a lot of great things in science. Whereas the guy that got the first place, he went on to train people how to pass that test, and that's what he spent the rest of his life doing. He didn't really contribute much mathematically in terms of publications, or scientifically in terms of publications. But because he was that second wrangler, a lot of people looked down their nose at him. It might not have helped that he was Scottish, and pretty sure it was Scottish. Now, I know so little about Great Britain that I sometimes will say someone's Scottish when they're Irish or something. But yeah, he's a Scots. Uh, and there is a prejudice there. So that was part of the problem as well. But ultimately, it was thanks to what historians have now called the Maxwellians. There was these four people, one of which was Oliver Heaviside, who made Maxwell's work so famous and interpreted them in such a way that we could now doing it. And in fact, invented what we now call vector calculus. One of those co-inventors was Oliver Heaviside that I just mentioned. Another one was a guy in America. Dang it, I just lost his name. He's one of the, I want to say it's Gibbs, Jason Gibbs from America. It's one of the free energies that you can find in thermodynamics. So one of those guys invented vector calculus, and actually published it, published parts of it before Oliver Heaviside did. So he gets more of the credit. But Heaviside, who had a sixth grade education, basically was a brilliant mathematician, and developed the Maxwell's equations in this vector calculus form, and made them popular for everyone. So that's the history that we're going going on here. And that all started because one, Galvani discovered the galvanic process by seeing frogs, dead frog legs twitch, and Volta put together a pile of batteries. And that's why we often use the phrase pile when we're talking about, for instance, a nuclear power plant that was made at the University of Chicago under their football stadium. We called it a pile. And that's also why we have a diagram for a battery that looks like a line, a shorter line, a line, a shorter line, a line, a shorter line. And for instance, I was just looking at my Hayes manual for my F350 and looking in the wiring diagrams, and I noticed that sure enough, it had six sets of short line, long line, short line, long line, short line, long line to represent a 12-volt battery, which was kind of interesting because I teach this, but that's basically one of the ways we can specify what the voltage of of a AC or a DC system is by the number of lines. So that led us to be able to study current because it turns out when you put a conductor between the positive and negative sides of a battery, the current, traditional current that we talk about, will flow from the positive side to the negative side. Now, Benjamin Franklin gave us the idea of positives and negatives of charge, and Benjamin Franklin was another person who didn't have much mathematical education. But what he did know very well. For instance, he was one of the first people, if not the first person, to estimate the size of the atom, and he did so by measuring oil spills in the ocean. He made the assumption that an oil spill on the ocean would be essentially one molecule or atom thick. And then all you have to do is take the volume of oil and divide it by the cross sectional or the surface area of the oil, and that will give you the thickness. So that's one of the things Ben Franklin did. But he knew that there was two flavors, if you will, of charge, and he decided we should call one positive and one negative, and he was the one that ultimately gave us what we chose as positive and negative. And it turns out that he had a 50-50 chance, and he missed it. The one that he thought was moving around and labeled the positive one turned out to be, in fact, wrong. It was, in fact, the negative one that moved around, and it actually goes from the negative side of batteries towards the positive side. But unless you're doing a very specific type of measurement, that was done and it's called the Hall effect, Hall effect. You can't tell the difference which one's which. So it's perfectly fine to pretend that circuits have positive charges. You can actually pretend like they're coming out of the positive side of the battery, entering the wire, going around the wire, and then coming back in the negative side, even though we know that in general they are not coming out of the battery at all. They're not even necessarily moving very far within the wire. Okay, but that's what we know, and it's perfectly fine to pretend that they're positive charges going around, or you can do the other way, but all the equations and all the stuff we use is based on the idea of conventional current, which sees positive charges leaving the positive terminal of a battery going to the negative terminal. Now, in addition to that, you have to have something that brings this energy because the voltage is obviously related to energy. If you're picturing, for instance, something being near a positive thing and being compelled to move, then obviously that positive thing's giving it energy in some sense. And that energy, once that thing gets back around to the negative, that energy is much less. How did that thing that had that energy get to a smaller energy? So it's not enough to just have a battery and a conductor. You also have to have some kind of component that could bring down that voltage. Ultimately, as we've learned now, this voltage is just potential energy per unit charge. Remember, the volt is a joule per coulomb, so it's really a potential energy per unit charge. But in order for us to go from the voltage of a battery, which let's say a voltage of 9 volts is a typical battery voltage, you know about the little rectangular ones that go on your smoke detectors, for instance. If you were to take the black probe or the black COM port of a multimeter and touch that to the negative side of the battery, and then take the positive probe that's connected to the V omega side, it'll have V omega because you can measure resistance or voltage voltage with it. If you take that red side and touch it to the positive side, that would read 9 volts on a 9-volt battery. Now, if you touch it just a centimeter away on wire where there's no other resistors or anything between it and that spot, then it'll still read very, very close to 9 volts. And in fact, because generally the resistances that you put in a circuit are way bigger than the resistances of the wires themselves, the wire resistance is usually negligible, so that you can imagine going from the positive end of a circuit all the way around the wire, around the wire, around the wire, and then back up to where the resistor is in the circuit and touch that red probe from the multimeter to the left hand side of that battery, or excuse me, to the left hand side of that resistor, and it'll still read very close to 9 volts. If you could measure it to say, 5 or 6 decimal places, it might very well say 8.9993 or something like that. But that's because everything other than semiconductor or other than superconductors have some resistance. So the resistance is the thing that we need to bring the voltage back down. So you can sort of picture a resistance as something like a set of stairs. You can picture the battery as sort of like an escalator where little positive charges come into the bottom of the battery, which would be the negative side of the battery. They ride a little escalator up, and now their height is, let's say, 9 volts. And they ride around the wire and they stay essentially level. They're gradually going downward, as I said, because once you get to the other resistor, the voltage might actually be 8.99993 or something. So obviously they're tilted a little bit, but it's a very gradual tilt. But you would keep it roughly 9 volts high all the way to the top of the staircase, that staircase being a resistor, and then the resistor being a staircase imagines the little charges, positive charges, walking down the staircase until they get to a height that's very, very close to 0 volts. Obviously, again, it should be maybe 0.00001 or something because the wire has some resistance. So now at the end of the stairway, the voltage is not 0, it's 0.0001, but you go almost horizontally back to the other side of the battery, and you're back at 0 height by the time you get to the negative side of the battery, which is the escalator going up. So that's a way you can sort of repeatedly think about current. That's the actual positive charges flowing around like water flowing through a water hose. Voltage, that can be thought of as a height, and then resistances acting to bring the current down. And a picture that a lot of people have seen in community colleges, in training programs, ECPI, also in electronic shops, is a little picture where they'll have like resistors pulling on a rope and trying to pitch down a wire or something like that. That's sort of what happens because it turns out that there's this law called Ohm's law, which says the voltage is equal to the current times the resistance. And what that means is once you take a battery, let's say 9 volts, and you connect it to a certain resistor, that resistor dictates how much current can go through it. And the bigger that resistor is, the smaller that current will be. Once you have that established from V equals IR, then you can realize that, not only does the resistor restrict the amount of current that can leave the battery, but it also is the thing that brings the voltage down from 9 volts to 0. Okay, so that's a big picture of electric cells and batteries and stuff like that. You can see, for instance, your book has some really good descriptions of how modern batteries are made. For instance, it shows a carbon electrode, which is often what we use now. In fact, if you've ever opened up a D or a C battery, I've done this. You're not supposed to, but I did it back when I was young and stupid and curious and willing to try stuff that I'm not necessarily supposed to do. I really didn't know it wasn't anything that you were supposed to do, but I did pull one apart and I found a lot of black stuff. And it was black stuff right down the middle. And for a long time, I didn't understand why that black stuff was in there because it didn't look. I mean, if you've ever looked at graphite and stuff, it does not look like a conductor. carbon does not look like a conductor, but it is somewhat of a conductor. So it turns out normally they'll have the positive pole on the battery. So, if you're talking about like a C or D battery, it's basically a cylinder with a flat spot on the bottom and a nipple on top. Well, if you pop that metal cap off of the top, assuming you could, it's actually a little bit more difficult than that. You first got to take the outsides off, the sides off, and then pop the top off. What you'd find in that little nipple is a black carbon rod that sticks down inside, and what you'd find inside of what the actual carbon is going inside of is some paste. And that paste is usually a not an acidic but a basic solution. Your book shows you one that is a sulfuric acid battery, and that has a carbon electrode that acts as the positive terminal and a zinc electrode that acts as the negative terminal. By adding an acid, you have a lot more free ions in the liquid compared to the water or the apple juice that I told you about before. In fact, just to give you a perspective why all those different juices work and why I know they work, I have actually had my students make batteries out of potatoes, out of apples, tomatoes, lemons, oranges. And in those cases, all I had to do was take the fruit or vegetable or whatever I was using. And I went to Home Depot and bought some number 10 wire, copper wire with no housing on it. And I bought some number well, no, 16 penny nails. I bought some 16 penny galvanized nails. You can take the 16 penny galvanized nail and jab it in one side of the fruit or vegetable, and then take the number 10 bare copper wire and stab it in the other end. And lo and behold, you'll read about zero point 0.7 volts just from those two. Now, if you take that zinc and connect that to a copper wire sticking out of another fruit or vegetable, then you can span across those two fruits or vegetables and get more like 1.4. And if you did three, you'd get more like 2.1 volts and stuff like that. So that's another way you can make it as well. Any questions on how that works? You might have already done some of this yourself.
No questions, please.
Okay. So it does have that, those pictures. It also talks more about, they normally say alkaline batteries, and alkaline is a more ancient word for basic. So when they say alkaline, that just means the opposite of an acid battery. Uh, and battery technology is a big thing. That's obviously partly how Elon became so wealthy is he's really hired some talented people, and he probably knows a lot of stuff himself, and has created a really wonderful series of batteries and battery technology, and even the charging mechanism between him and his employees has made a charging mechanism that the whole world could use. So that's all important stuff, and it's all related to it. But now we need to go on and talk more about the mathematics and the problem solving that goes on. So now I've talked about I've given a little bit about voltage, I've given a little bit about current, and I've given a little bit about resistance. But we need to go to defining what current is, and then Ohm's law and that sort of stuff. So I'm going to go ahead and turn on my iPad and get ready to share the screen with you. Actually, I didn't know it was off, or I would have done this a bit earlier. So we have to talk about, like I said, Ohm's law, which is basically V equals IR. We have to talk about the definition of current, which is going to be I is equal to dq dt. And then with that, we're going to, sorry, I'm pulling my notes up. Then with that, we're going to show you how to use those equations repeatedly to do various calculations. And I completely opened up the wrong file here. I'm going to my good notes now to pull this open. Hopefully it will open in a second, and I'm going to go ahead and share my screen while I'm waiting for this. Advanced iPad share. Uh, and I'm going to now go to, all right, it's not coming up. Okay, now it's finally coming up. I'm going to share the screen. Now, this screen is going to be really funky because I've got a bunch of other stuff on it, but it's all good. So I'm going to move on back. This is the notes I had from previous class, 241 class at that, but I'm going to go on and start moving from here. So first off, what I want to tell you is what a circuit looks like. So we're going to start off with a battery, and a battery can be just this, where this positive side indicates this long side indicates the positive side of the battery, and the negative one is the short side. But as I showed you, sometimes the battery is drawn like this, where you have multiple shorts and longs, in which case, again, the negative side is the side with the short side, and that's what a battery looks like. It could also look like this, where it's just one. That's acceptable as well. But the main thing is that's what a battery looks like in a circuit. The line that I'm drawing away from the battery, we have to interpret as a wire or some kind of conductor. And then that wire or conductor can run into something that I said was sort of like a set of stairs to bring the voltage down from, 9 volts to zero. That wiggle that I just drew there is the symbol for a resistor. So this is a resistor, and the symbol we use for that is R. And this is a battery, and the symbol we use for that value is the voltage is V equals, we could say like V0 equals 9.00 volts. And we could say the resistance is equal to 100.0, oops, point 0 ohms. That's the Greek letter omega. That's the capital Omega, as in I am the Alpha and the Omega. Remember, the New Testament was written in ancient Greek, and Alpha is the first letter of the Greek alphabet, and Omega is the last letter of the Greek alphabet. So that's what that is related to. And it turns out that Ohm's law can be interpreted many, many ways, but Ohm's law is this: V is equal to I R. And when I say it can be interpreted in many ways, you can interpret it like V is the change in voltage across an object whose resistance you call R when a current you call I is going through it. Okay. And in that case, there's a lot of different things that could mean R. The wire itself could be a resistor. You could also look at it in some sense, and a diode might be something you call as a resistance because actually a diode does have some resistance. So, in that loose interpretation, R is what you multiply by I to get how much the voltage changes when you go across an element in a circuit. So, that's sort of the more general, wide open version of Ohm's law. Another version or another way of looking at Ohm's law is you could say there exists specific things in nature called resistors that have a fixed resistance R measured in ohms, OHMS, and those things always have, assuming they're not screwed up, messed up, or burn out or whatever, always have a resistance given by R. And if you multiply that resistance in ohms by the current in amps, you'll get the voltage across it. In other words, all you have to do is, if you know the current coming into a resistor, you take that current in amperes and multiply it by the resistance in ohms, and the number that comes out will be measured in volts, and that will be exactly how much the voltage changes in going through that resistor. Now, the big thing to remember is yes, there are things like that, and you've probably seen resistors before. They're normally like a khaki colored with a bunch of different color stripes around them, and the stripes tell you, how big the resistance is, but they also have a power rating associated with them because if you actually exceed the power, then they'll fail and they will not have the resistance that they claim to have. So just keep that in mind. Remember, V are delta V, we defined as the negative integral of E dot dl, which doesn't mean too terribly much in this context. I just wanted to remind you where it came from. And because of that, what we ultimately know is the units of the electric field are volts per meter, but also we know that the units of volts are volts, which is equal to 1 joule per coulomb. So this is the joule of energy, and this is the coulomb of charge. Okay. And volts, of course, which now, because I put a 1 on it, it's not really meaningful to call it volts. It should be just volt. So I'll do that. So that's what the unit of volt is. I'm going to define as on average, I is a measure of the amount of charge, which you might call delta Q, that passes a particular point in a circuit during a particular amount of time, delta T. And if that's the case, you can see that remember when I put boxes around stuff, this refers to me either talking just about the dimensions of the quantity or the units of the quantity. I'm using it here as units. You can see, has to be in coulombs per second. And it turns out we're going to define 1 coulomb per second as 1 ampere. And the abbreviation for that, of course, one of the abbreviation is the amp, and another abbreviation is just capital A. Okay, but you can see the amp is a coulomb per second. And then finally, R, which if you're just talking about a chunk of material that you're using, then there's a very specific formula that allows us to calculate what that resistance would be. And that resistance is very easily argued from first principles just by thinking about trying to get people to go down a hallway. If you're trying to, let's say, evacuate elderly people in a home prior to a storm or something, you want to think what makes it harder for these elderly people to get out of a hallway. The thing that makes it harder provides more resistance. So if the hallway was really long, you'd expect the resistance to be high. So we're going to say resistance is directly proportional to length. Now, the other thing is if the hallway is just a doorway, you know, 32 inches wide by 7 feet tall, then you're going to have to go one person at a time. That's kind of slow. But if it instead was, let's say, 72 inches wide, you could fit two or three or maybe even four people abreast of each other walking through. Not only that, if you allowed it to be instead of 7 feet tall, 14 foot tall, and maybe you added another floor up there so we could walk them out down here at the bottom as well as the middle as well as the top, then what you see is the bigger the area of the hole, the smaller the resistance. So since a bigger area makes a smaller resistance, you want the area to be in the bottom. So that's what we find out. And then you say, okay, well, in terms of walking people down a hallway, obviously a longer length makes it harder, and a smaller door hole makes it harder. Those are obvious, but you could also think, well, what is it like in the hallway? So now if we jump from the idea of a hallway back to material again, there's some materials that turn out to allow electricity to flow really easily, and we call them conductors. And then there's other materials that require a great voltage to make current flow, and we would normally call those resistors or dielectrics. And to be honest with you, there's technically a spectrum that goes from the, you know, uh, vacuum, which would allow almost nothing to just flow by itself, to, something that allows it to flow really easily, like gold. Okay. So if you allow there to be something called the resistivity, a measure of how resistive a particular material is, then you could say, well, I'm going to define the resistivity such that if the resistivity is high, the resistance will be high. If you do that, then oops, then what you're going to do is put a rho right up there with the L, because a big rho and a big L both make a big resistance. Whereas a big area being on the bottom, big area makes a low resistance. They're thumbs up, thumbs down. Remember, I use thumbs up, thumbs down whenever you have an equal sign separating two variables, one variable on one side of the equals in the numerator, but the other side has the other variable in the denominator. So if you have them on opposite sides of the fraction and opposite sides of the equal, they're thumbs up, thumbs down. But if you have them both in the numerator on opposite sides of the equal, they're thumbs up, thumbs up. Or if you have them both in the denominator on each side of the equals, they're thumbs down, which is the same as thumbs up, thumbs up. So when you come up with this sort of thing, at least like we did in high school algebra 1, we would say the resistance is directly related to the length. You'd say, okay, well, R is proportional to L. And then if you wanted to make that an equation, you'd say R equals some constant times L. Well, that's more or less what we do, except we decided to not make another constant. We just stuck the constant row and made sure that had the appropriate numbers. So this became the resistance is equal to rho L over A. So that's a very important equation that we can use over and over again to figure out the resistance of a particular material, because in your book they have a table of resistivities. That's the row, resistivity. And I'm probably talking to electronic technician or electrical engineer or something right now, and you're probably feeling like an idiot for me telling you all this crap, or you're feeling like I'm an idiot for telling you all this crap. I apologize if that's the case.
Not the
This
case.
quantity. Are you an electrical engineer or something?
No, I am not. I'm
Okay,
an
good. That makes you feel a little better. We learn a lot about electricity and magnetism and circuits and stuff in physics, but not nearly as much as electronic technician or electrical engineer or any of that kind of stuff. Though I did have to take the electrical electronics engineering course, which is more or less the AC and DC circuits that you cover in engineering in your third year or something like that, or maybe your second year. So, anyways, that's the resistivity. The units of resistivity, by the way, if you look at this, you should be able to figure that out. So I highly recommend, before I give you this answer, that you look at R equals rho L over A, and you know that R is going to be measured in ohms, like that. Okay. So, given that R is measured in ohms, I suspect you know what the length of a wire would be measured in. I suspect you know what the cross-sectional area of a wire would be measured in, and therefore you can come up with the units of rho. So, definitely try that before I give you the answer if you haven't already. But just to let you know, the resistance, or excuse me, the units of resistivity have to get ohms out. So it's got to have an ohm in it, but it's also got to cancel out a meter in the numerator and a meter squared in the denominator. So it's going to have units of ohms times meters. Because obviously, if a ohm times a meter was divided by area, that'd be an ohm per meter. And then if you multiply that times the length, you just get an ohm, which is exactly what we expect. Okay. So that's that formula. This formula over here is important as well, but it becomes a little better by saying I is dq dt. So I will box off this formula as well as an important formula. And then there's another important formula, and this one is called Ohm's law. Okay. Remember, just as a recap, I is current and that's measured in amps. R is resistance, and that's measured in ohms. Rho is resistivity, and that's measured in ohm meters, which I couldn't really fit there, so I should probably do like this. I'll make the resistivity a little smaller. Whoa, or I'll just cut off the head of my row. There you go. So rho is resistivity, V is voltage, also called electric potential. I don't know that I would really say it's called tension, but I do know that often they'll say high tension lines when they mean high voltage. I don't know if that's just historically because they put them up so high and then they had to put them in under a great deal of tension, or if in some other language tension meant voltage. I'll just remind you that verbally, and I will say that it's electric potential, and I won't really use that phrasing. I just wanted you to know that it exists, but it's measured in volts, which equals volts, which, as we said, is a joule per coulomb. And I should also say that amps are coulombs per second. So now that we have all this information, we should be able to do some fairly decent, simple calculations. Let's start with example one. Example one is a steady current of, whoa, that's a bad looking F, of, let's say, 3.54 amps. Uh, travels along a wire for, whoa, Nelly, 3.00 minutes. A, how much charge traverses the wire? And B, how many electrons is that? Okay, so solution, what we know is I on average is equal to delta Q over delta T. And we also know that E, the charge of an electron, is technically magnitude-wise 1.602 times 10 to the negative 19th coulombs. So for part A, we're going to say I is equal to delta Q over delta T. And you know me, I tend to like to solve things algebraically first and then plug in the numbers. Feel free to plug in the numbers immediately and then solve for the variable. In this case, I'm solving for delta Q, and that's going to be I times delta T. And of course, the I is 3.54 amps. And remember, an amp is a coulomb per second. So I'm going to go ahead and change that now because it's going to come in handy in a second. The 3 minutes is 3.00 minutes. but you have to convert that to seconds, or else the seconds won't cancel out in the amps, which are coulombs per second. So what I do is I realize that 1 minute is 60 seconds, and the minute is in the numerator. So I might put that over 1 to realize that, and then I'll say 60 minute, oops, excuse me. I'll say 60 seconds is equal to 1 minute, like that. Now you can see that this minute canceled out with that minute and left just a second. So now when I multiply these quantities, well, once I turn my calculator on, whoops, now it done changed colors. So now that I've turned my calculator on, I'm going to take 3.54 and I'm going to multiply that by 3, and then I'm going to multiply that by 60. And evidently I typed something. Oh, yep. So 3.54 times 3 times 60. And this gives me 637.2. Obviously, the 60 seconds per minute was an infinite number of decimal places, but the 3.54 and the 3 were only 3 sig figs, so I'm carrying 2 extra digits now. And we can see that this second, by the way, did cancel out with this second down here, and therefore the result just came out in coulombs. So that is our actual answer for part A, is that 3.54 amps flowing for 3 minutes is 637 coulombs. For part B, we want to figure out the number of electrons. So I'll say the number of E minuses is equal to delta Q divided by E, which is measured in coulombs per electron. So we could actually, instead of just calling it E 1.602 times 10 to the negative 19th coulombs, we could say E is 1.602 times 10 to the negative 19th coulombs per electron. Okay. Now, remember, it's technically has to have the negative if you're talking about that, but we're just looking for the number of time the magnitude goes into it, so we're not going to quibble on that. Now we can go ahead and write 637.20 coulombs divided by 1.602 times 10 to the negative 19th coulombs per electron. And now you see the reason for me actually writing coulombs per electron, because the units is actually going to come out now in units of electrons. So 637.2 divided by 1.602 times 10 to the negative 19 gives me 3.9775 times 10 to the 21 E minuses. And that's with 2 extra digits. So we can say the number of electrons is equal to 3.977 space 5 times 10 to the 21 electrons. So almost a mole of electrons are passing through this wire in that 3 minutes. Any questions on that one?
No questions.
Okay. I do want to point out your book does a conceptual example, reminding you how to connect a battery. So just as a point of that, in case you haven't had enough experience in your lab yet, if you did have a battery, one thing I want you to understand is on these batteries like the AA, the AAA, the C, and the D that are cylinders, what you want to understand is that the terminal on the bottom, actually, I want to use a different color than that one. Down here is the negative terminal, and up here is the positive terminal. And also, I should say that AAA, double A, C, and D batteries all have a voltage of 1.50 volts. That's what you expect of them, but when you first buy them, they usually run anywhere from 1.65 volts to 1.72 volts, somewhere around in there. Uh, and ideally, you're supposed to be able to count on them delivering 1.5 volts. So that's what they are. Now, as far as connecting them goes, there's a bunch of different ways you could do it, but you could actually imagine to connect a light bulb, for instance, which luckily you guys have had a lab where you did work with a light bulb, and you probably learned how the light bulb was connected. I'm going to imagine this is a light bulb, and what I want you to think of is this little metal casing down here at the bottom that's normally threaded. It also has sort of a little circle of material and then another little circle of another material down at the bottom. What I want you to think of is inside of here, there is a wire connected to the threads. And then now that we're looking at the glass part, you can see the wire does something like this. And now it goes all the way down and touches that bottom part. Okay, that wire is often, with an incandescent light bulb, is often tungsten, and it doesn't have any polarity. You can connect the positive to the threads and the negative to the bottom of the light bulb, or you can connect the positive to the bottom of the bulb and the negative to the threads. Doesn't matter at all. What happens is, as the current flows through there, the tungsten gets hot, and once the tungsten starts to reach about 3,000 Kelvin, it will actually glow red hot. And if you go farther, it becomes white hot, and white hot just means basically the temperature at which the maximum amount of radiation comes out occurs at a wavelength that is way beyond the ultraviolet. So you're actually seeing the light come as if it's purely white because it's technically a color that you can't see. But the way you could connect that is you can, for instance, take a wire, connect it to that little bulbous part at the bottom, and do this. And then you can take another wire and connect it here like that. But the main thing you're trying to get from this is to understand that you have to have a route where you can imagine the positive charges leaving the positive terminal, going through the device, and then re-entering the negative terminal. If you don't have a way there and a way back, it's not necessarily a circuit. Okay, so that's what your book is doing by showing you all those different orientations of light bulbs and stuff like that. And in fact, ultimately, the one they choose has the light bulb sitting right on top of the battery, so that the positive technically is touching the bottom of the bulb, and then it has a wire running from the threads of the bulb down to the negative part of the battery. That works as well. I just showed it to you via wire. So just remember, you have to have a way for it to leave the positive terminal of the battery, and then a way for it to return to the negative terminal. All right, so that's another example knocked out. Oh, I'll also tell you, uh, this is a diagram for ground. And ground also means V is equal to 0 volts. Okay, so that's another circuit item that you're allowed to have. Sometimes they'll even just do it like that. That works as well. That's also a ground. the main thing is you're allowed, just like when we learned in conservation of energy and potential energy. Remember how you were told that you could make y equal zero so that the potential energy is equal to zero at any height you want, long as you stuck to it, it'd be fine. The same thing is true here. You can technically put a ground excuse me, at any one point in a circuit, and from there on out, that one point in the circuit is has a voltage of zero, and everything else will be a voltage different from that relative to where it is. So that's another thing to keep in mind. In fact, I often picture when I have a circuit like this, one that I have here, I often picture it as if this right here is the ground. And then I draw my bubbles. Remember, I told you about taking a multimeter, like a voltmeter, and you set it on volts DC, and then you have a black terminal that is COM, and then you have a red terminal, which is V omega. If you take the black terminal and connect it to here, then you can take the red terminal and connect it to various places, and out will pop a bubble. This bubble says 9.00 volts. This bubble, if we went from here to here, would probably say 8.9997 volts. Okay. And then right here, this bubble, again, I'm drawing them as bubbles because that's what I'll be using in class a lot of times. This bubble would read 0.000 maybe 1 volt. And then, of course, this bubble would read zero point 0.0 volts. Okay, so that's just another thing we sometimes use uh, when we're trying to work out, what's the voltage at a certain point in the circuit, or how much current is going through a certain resistor, or how much charge is going to a certain capacitor. I often will take bubbles like that and place them around, place them around the circuits. What I want you to think of whenever I draw one of those bubbles, I want you to think of this diagram where I've got the ground right up against the negative side of the battery, and I've also got the COM port right there at that same spot, and then the red is just poking certain spots, and up pops a bubble. Okay. So, anyways, hopefully that helps you when we go a little further. Now that I've covered all this sort of stuff, I want to talk a little bit about. Oh, I actually almost forgot this. There's an exercise your book has, and it's actually very fruitful. So I want to make sure we do it. It's called the amp hour. Have you seen amp hours anywhere lately in stores or anywhere?
No,
No.
uh,
You will now, trust me. It's kind of a crazy thing, but next time you get in a line at Walmart, for instance, or Target, you'll see something like this guy that's basically a battery pack for charging your phone. And it'll say like 100,000 amp hours or 10,000, actually, it'll probably say more like 10,000 amp hours or something like that. So I just want to point out what that is. What is an amp hour? What about and this one I've sort of already discussed, but I want to hit it again. What about a kilowatt hour? Okay, those are two different things. Uh, for instance, 1 amp hour is equal to one, and I'm going to go ahead and write it out so everybody knows what we're saying. 1 amp hour is equal to 1 coulomb per second times 3,600, or excuse me, yeah, 3,600 seconds, because remember, an hour is 60 minutes, and 60 minutes obviously can be broken down into seconds, and each minute is 60 seconds. So 60 times 60 is 3,600. So you see that when you multiply 1 hour times an amp, you get 3,600 coulombs. So that's what an amp hour is. An amp hour is 3,600 coulombs. Remember, a coulomb's a butt ton of charge. It's not unreasonable for a lightning strike that could kill someone to deliver no more than 100 or even 500 coulombs. So 3,600 is a buttload of charge. And when you talk about, for instance, this device, which I of course got from the completely above the board, awesome shopping experience that is the TikTok market. This one specifically says 40,000. Yeah, this is 40,000 amp hours for this one. It's actually got a solar panel on the front, so it charges by itself that way. And it also has three little ports on the back. But that one holds 45,000 amp hours. So you can imagine 45,000 times 3,600 coulombs. That's a lot. It doesn't mean that much to you until you look up and find out exactly how many quote unquote coulombs it takes to charge an iPhone. And then you see that, 45,000 amp hours can probably charge, 20 uh, uh, iPhones. Now let's talk about the other one, the kilowatt hour. This one you're probably already familiar with because you're a grown person that's probably paid an electric bill or two. And when you pay an electric bill, you know that you're buying kilowatt hours. So let's do that. 1 kilowatt hour. Now, they often just write it like it's a hyphenated word, but I want you to understand that it is technically a multiplication. So it means 1 kilowatt times 1 hour. Okay. Now, a kilowatt is equal to 1,000 watts. So a kilowatt hour is equal to 1,000 joules per second, because that's what a watt is, times 3,600 seconds. So again, you see the seconds cancel out. And because of that, you get 3.6 times 10 to the 6 joules. So it's literally 3,600,000 joules. That is what you buy from the power company. Typical rates used to be on the order of 8 or 9 cents per kilowatt hour. I think they might be closer to 9 or excuse me, closer to 12 or 15 right now. I haven't looked at one in a while. I should have done it today, but I forgot I was covering this, so I didn't. So 3.6 million joules is how much energy you get. And you probably, like me, if you've been paying bills for a while, electric bills, you think electricity is expensive, and it is. But if you remember that I teach my students that 1 joule is about as much energy as required to lift a nice, good, delicious, moist. A lot of people hate that word moist, so I gotta use that every now and again. Red delicious apple. If you lift one of those up from the floor and lay it on a kitchen table, that took about 1 joule of energy. So when you look at 1 kilowatt hour of energy, that's basically enough energy to lift 3.6 million apples from the floor to the top of a kitchen table. Now, if you had to pay humans to lift 3.6 million apples up from the ground to the table, I'm certain you'd pay way more than 15 cents. So that's the sense in which I said electricity is not that expensive. But that's the only sense. Any questions on that one?
Nope, no questions.
All right. So Ohm's law and resistors. Now I want to show you a little bit of what that means. So, and we've done this in lab, or I'm pretty sure your lab has too. But one thing that you should notice is V is equal to IR, and I want to remind my students both my 241 students and my 242 students that one of the things you're supposed to pick up, especially from our labs at TCC, is that when you graph something and compare the theoretical function that you have that explains it to y equals mx plus b, you should be able to understand which one's playing the role of y, which one's playing the role of x, and then more importantly, what's the slope and what's the intercept. So the equation for a straight line is y equals mx plus b. So I want to remind you all that when you make a plot, if I want to, and I'll put you on a spot a little bit here. I won't say your name just in case you don't know. But if you wanted the resistance to be the slope of this curve, do you know whether you'd put V or I on the vertical axis?
So you said resistance to be the slope.
Yes, if you want resistance as the slope.
I think that V would be on the vertical axis.
Excellent. Very, very good. That's one of the things my students aren't getting as well as I'd hoped. That's part of the reason why I'm bringing this up. So if you put the I over here and the V over there, remember the vertical axis is the Y. So since we claim that, what I'd do is I'd write V under the Y. And since I'm putting the I on the horizontal axis, I would put the I under the X like that. And then you'd see that whatever I have to multiply by the I, which in this case is R, that's got to be that's got to be the slope, and the intercept is got to be 0 because there's just plus nothing. So yes, you're right. If we made a graph like this, then this slope is equal to the resistance, and it's in units of volts per amp, which turn out to be ohms. Now, it turns out you can also have items that do stuff like this, in which case we can default to the more open example of Ohm's law, in which the slope right here happens to be one resistance, but the slope right here happens to be another resistance. So that's the another way that you can actually interpret Ohm's law. Now we've actually run out of time, and that's fine. I will cover more of this later, and we'll do more examples. But that's good enough for right now. We are just up to like example 25.3, so that's the next thing, the next type of calculation we're going to do, and I'll probably finish up chapter 25 next time. Thanks for coming, Matt. I will wait in case you have any questions, but you're free to go. Would help me if you go ahead and send a chat with your first and last name just in case I need it for roll. I'm sure I won't remember who's here today.
Yeah, sure thing. I'll chat it now. I'm gonna jet for lab, but I'll chat it over to you now.
No problem. Good luck, bud. Have a good one.
Yep, thanks a lot.
You're welcome. Bye bye. All right, so that's it, and hopefully everybody got something out of that. I know I tell a little bit more history than necessary, but I think that part's kind of interesting, and I think it's good to hear those sort of things. So hopefully I didn't waste too much of your time. I'll be making some more videos regarding this chapter, and we should finish it up next time. So thanks for coming, everybody. Bye bye.